So what I want to do first is introduce Mitsuhiro Kawase, if I'm saying that properly, who comes to us today from the University of Washington in Seattle. I was an oceanographer there in the Renewables group. He's originally from Japan. He did his bachelor's actually here in Sussex, then did his PhD in Princeton, a few years of postdocing at MIT, that little spot over there, and then he's been at the University of Washington ever since. And it's been 5 years since the group, this Renewable group, has been going. So with great pleasure, I give it over to you.
Thank you, Beth. Thank you for inviting me to visit here. It's a pleasure to be in this town, which is to be lovely. I gather you have a great weather this summer. Okay, so today I want to talk about tidal energy extraction, but from a very unusual perspective, perhaps from a very large scale perspective. So this may be something that many of you are quite familiar. So unfortunately, this webinar setting means that while I'm talking, I'll probably have to mute other people's microphones, so we can't really be very interactive, but at the end we'll put the microphones on. So if you could hold the questions to the end, I'd appreciate it. I'd like to acknowledge my co-author, Marisa Gedney, who was an undergraduate research assistant for me, who did most of the model runs that I'll be talking about today. And the work is supported by US Department of Energy, who has generously funded the Northwest National Marine Renewable Energy Center. So first I want to describe briefly what we do in University of Washington in Northwest National Marine Renewable Energy Center. And then I'll go into the talk proper. I'll talk about why I got motivated to look at tidal energy from the angle that I'll talk about today. I'll describe the setup, the model that I used to do this study, and model output, how I diagnose the model. And the main part of the model result is how tidal energy extraction looks like in the context of overall energy balance in the ocean or a subsection of the ocean. And then I'll briefly talk about modeling that was done with just subdomain of the model. The motivation for that I will also describe. This was presented at IMA conference last year, so some of you might have seen the results. And then I'll summarize the take-home points at the end and open myself to answering questions. We call ourselves Northwest National Marine Renewable Energy Center, or NNMREC as an acronym. And this center was established 5 years ago with support from the US Department of Energy. And it's actually a consortium of 2 universities. Oregon State University in Oregon, which is devoting itself to wave energy research, and as the University of Washington, which is specializing in tidal energy research. The URL is given at the bottom, dex.washington.edu/NNMREC. The reason we decided to specialize in tidal energy is that we have in our local waters probably one of the most promising tidal energy resources. We live in the town of Seattle, which is situated on Puget Sound, which is the southernmost fjord system on the Pacific coast of North America. This is a pretty long system. This is about 50 kilometers. So the total length is about 200 kilometers. It's also very deep. Maximum depth is 283 meters, which means that the deepest point of Puget Sound is deeper than the continental shelf. So it's a fjord basin that traps water as well. The thing that makes Puget Sound interesting from tidal energy perspective is that it has fairly large size resource at the entrance called Admiralty Inlet. and that's close to the population centers. So the resource is close to where the demand is, which is relatively actually unusual, I think, for tidal energy resources. A lot of resources exist in very remote northern waters, such as Aleutians. But bringing the generated electricity into where demand is going to be a problem. So the thing that makes Puget Sound very interesting is this close proximity of substantial resource and the demand. The sound as a whole dissipates about 700 megawatt of tidal energy. And this is about a benchmark that we think will give us the order of magnitude of the energy that can be extracted out of the system. Several hundreds of megawatts is certainly possible. If you really wanted to max out the generation, probably a gigawatt is possible. Now, in US, the average household consumption of energy is just about 1 kilowatt per household. So 700 megawatt of energy, if, let's say, if that can be generated, then that can power about 700,000 households, which is a substantial part of the Seattle metropolitan area, which has a population of something of the order of 2 million. So the resource is close to where the demand is, and that makes tidal energy interesting to us. Now, currently we have a plan to put in pilot scale devices into Admiralty Inlet, which is this entrance channel. And this one shows the peak current from the model. It exceeds 2.5 meters per second. It actually exceeds 3 meters per second quite easily. And the plan is to put 2 open hydro turbines, 6-meter turbines each, in this entrance channel by the end of 2014. It's one of these projects that's been pushed back and back and back because of very stiff regulatory requirements. We believe we have cleared almost all of the regulatory hurdles to put devices into the water. There are a couple of stakeholders who are still raising concern about this. One is the traditional Native American tribes who have fishing rights for these areas, and the other are underwater cable operators. Puget Sound is crisscrossed with underwater cables. They don't want devices of development close to where they have their cables. But still, we have a very substantial resource at the mouth of Puget Sound, which is fairly well characterized by now. So our main interest is really to go and help the developers put these pilot scale projects in and then make the measurements around it before and after, during and after the project to help aid them in developing the site further. So we've been doing a lot of resource characterization type measurements and monitoring, and we use a very compact tripod setup called the Spider, which is loaded with instruments, as you can see. We have hydrophones on it, which measures the ambient noise level in the water. We have specialized listening devices that, because the vocalization of harbor porpoise, there are other marine mammals such as orca that are of great interest and concern to us. We also have acoustic tag receivers for fish species. The hatchery fish are tagged with acoustic tags, so you can track their migration by sending signal out and listening to the acoustic tags. So that's great interest to us as well. We also measure water samples. And finally, we have an acoustic current Doppler profiler in the center of the setup to measure the currents. In some setups, we also had ADVs, acoustic Doppler velocimeter, to get high resolution measurement of turbulence as well. And this gives you the sense of the size of the instrumental package that we have. we've deployed this in Puget Sound waters for 5 years or so, and we have now gathered quite a long time series of various quantities of very high quality. And at the University of Washington, we have particular expertise in the area of underwater acoustics at the Applied Physics Laboratory. So we are particularly interested in making acoustic measurements, both of the sound and also of the currents. And these will be fed into a model of the acoustic environment, which is translated into a stressor level for the species that we'll be interested in. And out of which we intend to characterize the species specific behavioral impact, namely whether these devices generate enough sound so that their behavior is changed or not. Our regulatory environment is very, very stringent. For marine mammals in US, almost anything that could interfere with their behavior can run into these regulatory difficulties. So not just death or injury, but just even just a level of behavioral change could trigger regulatory no's. So we have to be very, how can I say, conscientious in showing to them that we are trying to address these questions. We have also done such things as materials testing on this tripod setup. These are 2 different types of materials that were mounted on this tripod and then exposed to the seawater for 6 months, I believe, in this case, or 9 months, excuse me. Yeah, and to show that some materials are quite promising, while others definitely have problems surviving in marine water conditions. And then we do a lot of oceanographic studies using numerical models, and this is the program that I'm particularly interested in. Puget Sound is a very deep system, so it has a potential of trapping water and contaminants, and water quality is a big issue. So here we've set up a very idealized model of ocean with fjord connected to it to see what kind of effect taking energy out will have on the fjord exchange circulation. And we haven't gone very far with this particular study, but one of the interesting things about marine renewable energy extraction is that it can create it can be a local source of turbulence as well as momentum sink. So locally, the mixing can be enhanced. At the same time, the exchange flow can be diminished. So it is not an obvious answer that taking energy out of the system would slow down the circulation and therefore create or worsen water quality problems. We also do realistic models of the region to come up with a more detailed map of resource characteristics. And here we have done a high-resolution model of that Admiralty Inlet channel using a 3-dimensional model to show on the left the kinetic power density, and on the right, this parameter is bidirectionality of the current. How much the flood and wave currents align with each other. If you have a ducted turbine that doesn't yaw, you would like that to align as much as possible. So this is one of the kind of qualities that we might look for in deciding where to site turbines. So from numerical models, we can map these and other parameters, and then we can overlay them on top of each other to find an optimal location for a tidal array. Finally, we have some interest in developing tidal energy or marine current energy at very small scales, mostly to help people power oceanographic instrumentation over very long duration out in the ocean. These are fairly small devices, like 1 meter large, which probably would produce several kilowatts of energy, that kind of level. But with these devices mounted on the mooring, then you can deploy the mooring for a very long period of time, let's say a year, with very high frequency sampling, provided that you also provide that mooring with the data storage capability or some kind of telemetry capability. Right now, this kind of thing is limited by how much battery pack you can attach to the mooring system. So mooring that can generate its own power will be very useful to oceanographers. So that's a kind of very broad survey of the NNMREC activities so far. And we're also diversifying into addressing fisheries questions and questions about the social and human aspects of renewable energy development. Okay, so that leads to the start of my talk proper. And I have presented this at last week at UTEC conference. So I came into the business of marine renewable energy from the oceanography side. I've been asked to help people with answering oceanographic questions. So I came in with the perspective of a physical oceanographer. And right now, there's a great deal of interest in marine energy, but from a very different point of view. People have become aware that tidal energy is the source of energy that drives ocean circulation at a very, very large scale. So the global scale ocean circulation, at least some of it, is driven by the energy of the tides. The ocean gains about 3.5 terawatts of energy from tidal forces of moon and the sun. Then it goes through various channels, and eventually about 2/3 of that makes it into coastal waters where they are dissipated. So by generating electricity out of it, we are diverting perhaps a very small portion of this energy that gets dissipated eventually in the coastal waters. We also become aware that this program contains many scales from a very large to very small scale. In particular, this gain of the energy from tides takes place basically at the global scale, because the scale is that of the astronomical forcing. So the tidal energy in this sense gains energy at the global scale, and then it redistributes and transport energy through long wave processes. These are waves like tsunamis that have, again, very, very large spatial scales. On the other hand, dissipation of this energy is highly localized. This is a diagnostic map of where the semi-diurnal tide is dissipated. You can see that hotspots exist along the coastal waters as well as mid-ocean ridges. But while the energy gain occurs at large scale, energy dissipation occurs at small scales. And elements such as Puget Sound receives that energy and is dissipating that energy in there. So, so this scale difference between the large and small is quite striking. And this poses one of the difficult questions, I think, is that when we study tidal processes in the coastal waters, we almost always use regional scale models. We certainly can't afford to model just the Puget Sound, or rather Puget Sound, but we really cannot include the entire global ocean. So we have to impose the tide as boundary conditions in some ways. But this tidal energy program, if you write down the global equation, it is such that the equation is global. If you change the tide in one place, the effect of that change in principle is transmitted and distributed around the globe. So it is not obvious whether a model that is limited in space has the correct physics for the use in tidal energy applications, in which you actively change the tide within the domain. There's a potential that that change of the tide would influence the global ocean and change this energy source down the problem. So, so I want to focus on two questions in this study. First of all, I want to look at and understand how tidal energy extraction works in the context of this energy balance. How does tidal energy extraction look like in the context of regional and global scale tidal energetics? And what useful things we, the tidal energy developers, might learn from such a perspective. And the second, more practical question is if there are any significant limitations to studying tidal energy with a regional scale model. And if there is, what is the uncertainty level associated with that? How much trust can we put in the results that comes out of regional scale models? So the approach we decided to take was to model a global system, but one that is highly idealized. So we decided to set up a very idealized ocean that is forced the way the real ocean is, that is forced by astronomical forces. So this ocean is 8,000 kilometers square ocean in both east, west, and north, south dimensions. It's about intermediate between Pacific and Atlantic oceans, although it doesn't extend very far into high latitudes. It is ringed by the continental shelf that is 200 meters deep. Deep ocean is 4,000 meters deep, which is the standard depth for deep ocean. So as I said, that tide is forced by astronomically by tide generating forces, which mimics the lunar force at 20 degrees declination. And then we attach a fjord-like embayment at the northeastern corner of this ocean model. This fjord is 200 kilometers long and 10 kilometers wide. It's too small to be shown on the main picture. We also did a case in which this entrance channel of the fjord is extended so that fjord becomes resonant to the semi-diurnal tide. The tidal energy extraction is simulated by increasing the friction over the sill of the fjord. This narrow channel is also shallow so that a strong current can be generated there. And then finally, once the global model is set up, we can take boundary conditions from that global model and then supply it to a model whose domain is restricted. These are more like typical coastal and regional models that we would use to study the regional scale tides. So by doing this, basically considering the global model as the truth and comparing the result of that with the regional model, we hope to come up with some measure of uncertainty associated with these regional representations. So let me start with how the tide works in this global model. On the left, you see the tidal elevation out in the open ocean. The right top is the tidal elevation time series at the head of the fjord. And then right bottom is flooded current as along the center of that fjord as you go into the fjord. So you can see in the open ocean semi-diurnal tide, it propagates around the rim, northward and then westward along the polar boundaries, and then eventually towards the equator. This is the sense of the so-called Kelvin wave, and is very much like the real-world semi-diurnal tide propagation. You can quite see that there's also diurnal tide present as well, and it's not very obvious from this, but diurnal tide takes more of a form of a standing oscillation between the two hemispheres. So you can see that in the fjord head, you have a semi-diurnal tide, but there is a small diurnal inequality in it. And then the ebb and flood current is enhanced over the entrance sill to about 1.2 meters per second. Not a huge current, but that's where we put the energy extraction array. Okay, so what we wanted to do was to be able to write a complete energy balance equation for this system. So that's what's done here, and I don't know. Don't worry too much about the symbols, but it's quite straightforward to do for a two-dimensional model. By the way, that model is two-dimensional, horizontal two-dimensional model, so-called shallow water equations, which conserve total mechanical energy, which is the sum of potential and kinetic energies. The energy balance consists of, for any domain, the change in the total mechanical energy given by energy flux across the boundary, the natural dissipation within the domain, energy extraction within the domain, and gain from the tidal, tide-generating forces. For the global domain, the first one is 0. And for the long-term average, if the total mechanical energy on average doesn't change, it would become three-way balance between gain, natural dissipation, and energy extraction. This first one thing that is important is that the form of this flux vector here, it consists of kinetic energy flux and pressure work. This quantity, if you are familiar with fluid dynamics, you might recognize as the Bernoulli function, and it consists of the kinetic energy flux and what is essentially potential energy flux. For tides, this second part, the potential energy part, is by far the dominant over the kinetic energy part. And this is sometimes unappreciated, I think, in tidal energy research by tidal energy researchers. Oftentimes, tidal energy researchers think of the kinetic energy density times velocity as a flux of energy that is coming into that area. But for a problem like tides, so-called low fluid number problems, this flux is actually subdominant to the potential energy flux. These two numbers, the ratio of these numbers, one form of what's called fluid number. And for the tidal problems, that number is always small. Something to keep in mind, I think, when people talk about tidal energy flux coming in as simply a product of kinetic energy times velocity, because that's actually very misleading. I fixed the natural coefficient of dissipation at 0.003, which is the sort of canonical value for this kind of study in coastal areas. But I changed the energy extraction coefficient to mimic different levels of energy extraction. If you like, this basically represents different scales of the array and put them into the system. On long-term average, as I said, the average change in mechanical energy is 0. So it becomes a balance between energy source, which is influx at the boundary and gain from tide-generating forces, and then dissipation, natural or man-made extraction. All of these terms can be readily calculated and diagnosed in a numerical model. We can write out a very accurate energy balance equation, at least in this idealized world. Many of you, I hope, are already familiar with how energy extraction works in a channel or embayment system like that. When you increase this energy extraction coefficient, initially that leads to increased energy being extracted out of the system. But as you do so, you essentially increase the friction in the system so that eventually it starts to limit the amplitude of the tides within. So as you increase the energy extraction, it doesn't increase indefinitely, but eventually reaches a peak beyond which putting more friction into the system simply leads to less amplitude of the tide and less energy being extracted. So this is a very typical energy extraction curve for a channel system or a base system that's been studied extensively by analytical means and others. Here I have plotted the tidal range and how that changes with the extraction coefficient. Initially there's a relatively little change, but as you approach this maximum, the tidal range is affected. And then once you go past this maximum, the more the larger the energy extraction coefficient, simply the amplitude decreases and less energy is taken out of the system. So you can plot these two quantities together and come up with a curve of energy extraction versus tidal range change. And again, these curves are familiar to people who have been studying tidal energy extraction and confirms the analytical formula very well. The only thing that actually was unusual about our model is this initial rather steep drop in tidal range as you start to extract energy out of the system. I have never seen this regime in any of the other studies, and I'm certainly not trusting of it. It could be something peculiar to the particular geometry we adapted, or it could even be some kind of numerical artifact as well. So I'm not believing that this regime exists, but it's a robust feature of all of the experimental series we've run with these models. So I can't really wish it away. But we'll look at how the energy extraction works at the maximum extraction and compare that with how the tidal energy works in the case of zero extraction. So first I'll look at the case where the estuary is a normal estuary that is not resonant at the semi-diurnal frequencies. And upper left, I have plotted energy flux into the fjord. This is integrated energy flux across the width of the fjord, going into the fjord. And it is plotted against the distance into the fjord. So this is basically where the sill of that fjord is. The blue dashed line shows the energy flux in the case of no extraction. The fjord draws about 163 megawatt of energy. And that flux decreases gradually over the sill region. It is broadly dissipated over the sill region by natural dissipation, which is plotted in the lower panel. You see a broad natural peak of natural dissipation over the sill area. So what comes in the natural state is mostly dissipated over the sill, where the current is strong, and relatively small amount goes into the interior basin. At the maximum extraction, and by the way, the maximum in this case was about 250 megawatt of energy. The fjord does draw more energy from the open ocean. It's about 274 megawatts. This flux though comes in fairly intact until it hits the tidal extraction array, where it is abruptly dissipated. It is almost in its entirety taken out by the extraction array, and less of that makes into the interior. Correspondingly, the natural level of dissipation decreases relative to the no extraction case. And this is because the natural dissipation is proportional to the cube of the velocity. And at the maximum extraction, we have reduced the tidal range quite substantially by about 40%. The velocity itself actually decreases by more than a factor of, by the same amount, and the power dissipated decreases by more than a factor of 2. So instead of the incoming energy being dissipated naturally, it is taken out by the tidal array. So this difference between the energy flux at the mouth of the fjord between the maximum case and the natural case is less than what the tidal array is taking out of the system. Another way of saying it is that what's being taken out of the system is in part repurposed from what is naturally dissipated within the system. One might ask, so where is this additional energy, about 110 megawatt of energy, coming from in the open ocean? So I have here plotted that energy flux and plotted the difference in energy flux between the maximum and zero extraction cases. one thing we notice is that there is an energy that appears to be sourced from local waters, mostly in this northeastern corner. But there's also flux change everywhere in the ocean basin. So here I have calculated this extra energy that was coming from certain distance away from the mouth of the fjord by integrating the flux across this quarter circle of distance r from the mouth of the fjord and plotted it against the distance from the fjord. And what you can see is that it does go through a zero crossing at about 2,000 kilometers, but then it goes large and negative. And it's only when this R reaches the other end of the ocean basin that this integral settles down. So at least in this way of looking at this, there's no obvious answer to the question, where is that energy coming from? You know, it's it looks like it might be sourced from local waters, but you know, but extraction has effect on tides. You know, minuscule effect, but its effect is global, and it is, you know, drawing energy therefore globally still. Why do we care about this? Because what's represented as natural friction, natural dissipation in this is actually a sort of blanket sum total of very complex processes that in which tidal energy is expended in the fjord, many of which goes into very vital processes within the fjord. For instance, tidal energy is the important source of turbulence in an estuary, and that, you know, therefore the important cause of mixing in the estuary. And then that mixing in turn has many important physical effects as well, such as maintenance of freshwater layers. If you have a fjord that receives substantial freshwater from the land, the maintenance of stratification is, or rather, the dilution of this freshwater is crucially dependent on the energy you put in from the tides. So if you divert that energy into energy extraction, then you might slow down processes such as Estuarine circulation in the system. So, so this diversion of the energy from natural to extractive could have important consequences for the estuarine ecology. Yeah, this process is basically all scale as cube of the tidal current. So that makes it very sensitive to small changes in tidal currents. There's some verbiage that I skip over since I'm running out of time. Let me now look at the case in which this fjord is quarter wave resonant. People suspect that such resonance may exist in, for instance, Bay of Fundy in Canada, or perhaps even Bristol Channel here in the UK. Now, in this case, the fjord at the maximum energy extraction actually draws less energy from the open ocean than the natural case. This might seem rather unexpected, but you can understand it because in a genuinely resonant system, it is dissipation that limits the amplitude of the tide. The other case, normal case, it is the frequency mismatch between the natural surge frequency of the estuary and the tidal frequency that basically sets the tidal amplitude. But in this case, the tidal system is resonant. Its natural surge frequency is the tidal frequency, and it's dissipation that sets the amplitude. That means any additional dissipation you add to the system increases the Q factor of this estuary and reduces the amplitude. And since energy extraction, energy dissipation is proportional to the cube of the amplitude, you actually, the maximum extraction case draws less energy from the open ocean. And similarly, you can see this energy flux making it to the array and then getting abruptly taken out. And you again see you have a large reduction in an even larger reduction in the background energy dissipation in the fjord. You can see this actually that in this case, if this flux change actually reverses, it looks as if the fjord is exporting energy. That's because it's actually importing less energy in the maximum extraction case. Let me move on to the energy, the experiments that we did with subdomain models. We've used two subdomain models, one that extends into the adjacent deep ocean, and we called it regional ocean model, and one whose extent is limited within continental shelf, which we called it coastal model. One is green and the other is red. So the red is the smaller of the two regional subdomain models. So I've been showing you the experiments of the full domain model, but we can also take the boundary condition from the full domain model to force the subdomain model, do the energy extraction with the subdomain model, and compare the two to come up with how much effect this restriction of domain would have on the on our results. Here I have plotted that energy extraction versus tidal range curve, but I've normalized it so that the energy extraction and tidal range are both given in percent of the maximum values. And for the three cases, as you can see for both non-resonant and resonant estuary, these extraction curves lie on top of each other. They agree very well with each other, which indicates that fundamental physical character of the problem is not compromised by restricting the size of the domain. What does change, though, is the absolute value of this extracted maximum. In the case of non-resonant estuary, it's actually interesting that the larger of the two domain models, you can extract less energy than the smaller domain models. I was talking to some people at UTech, and we think that is because in this particular model, these open ocean coast tidal waves are mostly restricted to the continental shelf. So it's mostly on the continental shelf that energy gain from the astronomical forces by the tide is happening. Similar kind of thing you can see in the resonant case as well. Although in this case, the coastal model actually does very well in terms of absolute numbers. Oops. Okay. No problem. Let me go back to see if I can find that slide. There isn't very much left. I think there are only 2 slides more. We've also looked at the effects of different boundary conditions, looked at the effects of whether or not include local tide generating force in the model. Typical coastal models do not routinely include local tide generating forces. Instead rely on the boundary conditions almost entirely. We haven't really seen very great systematics in this, and we haven't really wrapped our brain around to really think about this. The only thing I would mention is that at least in this context, it does seem that coastal model does better than the regional model. This was a little bit unexpected because much earlier study by Garrett and Greenberg, who studied the energy extraction in the Bay of Fundy, said that such model should at least include the adjacent deep waters. But in our case, it doesn't quite seem to be the case, but we don't quite understand why as yet. The other thing, the coastal model, sorry, regional model that is forced by this Chapman-Flatter boundary condition, which is a very popular boundary condition in regional tidal models. Without tide generating force, it actually does very poorly, and in fact, the tides, actual tide it generates is very unrealistic. Once you put tide generating force into that model, the result dramatically improves. Much better tidal validation as well as the energy extraction values. So I think tide generating forces can be quite important once I think the domain size becomes substantially large. Okay, so let me summarize what we have found so far. I think the most important finding so far is that the energy that tidal array is extracting from an estuary is in part repurposed from the natural energy dissipation in the system. So that has important implications, especially in the estuarine dynamics. In practical terms, I think that means that the models that we use to study tidal energy extraction, I think should have correct natural energetics. That is, it should be calibrated for how much energy it is naturally extracting, not just simply the amplitude of the tide or tidal currents. If we want to apply it, especially towards use such as environmental impact assessment. The limited domain representation does not seem to fundamentally change the physics of the energy extraction process, but introduces uncertainties up to 25% in the carrying capacity or the resource assessment of the estuary. And we think that this can be reduced down to about 10% by judicious choice of boundary conditions and domain size, and possibly including tide generating forces, which brings it down to about the same level of uncertainty associated with other issues within the model, as I talked to other researchers at UTech. But if you have 3 or 4 such issues, it's quickly adds up to 30–40% uncertainty. So which we need to. At this point, I'd say that regional numerical models of ocean circulation for this kind of study still has leading order uncertainties. Okay, that's the end of presentation. So I'll try to set it up for questions. Okay. On my end, I have unmuted all of the microphones. So,
well,
yeah.
Let me first thank you very much for that.
Thank you. Thank you.
Okay, while we're seeing if anybody from there wants to ask questions, can I see if there are any questions?
Yeah.
Okay, can I just ask what model systems did you use, and did you investigate the grid setup for kind of the results of investigation, whether that had effects, and whether there's any...
Yeah, the model, yeah. Okay, yeah, the model was implemented using the barotropic component of Rom's model, which is a very commonly used model. I'm pretty familiar with it. It's a very simple, though that part is simply a shallow water model. So I'm sure any well-implemented shallow water model can do the same. I haven't done something like a grid independence study by trying to see the convergence of the solutions. Although all the processes are very well resolved, so I'm fairly confident that the numerics are sound. I've also done things like propagating analytical solutions to make sure that the grid reproduces known solutions accurately. So, yeah.
Just as a follow-up, I was wondering whether the reason why the regional model doesn't perform so well is because the 2D solution might not actually do well at putting processes over the open ocean shelf edge correctly.
That I think it's an intriguing idea. Compared with the food restricted that way. But the other thing that I think is possible is that that edge or the southwest corner of the regional scale model actually lies very close to the semi-diurnal anhedonic point of the open ocean, and that may make the model very sensitive to small errors in tidal ocean. Anything else?
Can I ask a question? It's a very open question.
Yeah.
But then if you're saying that you think if you're modeling systems,
yeah.
you can get down to a 10% error issue.
Mm-hmm.
What then, going back to some of the graphs where you were showing sort of once you hit your optimum extraction and going down,
yeah.
what percentage is that then where you would say there is an optimum to extraction and all of the caveats?
Yes, let's see if I can address that question using a particular graphics. Let's take this picture here. In this case, the non-resonant case, the postal model has, I believe, about, at the peak about 15%, more energy being extracted out of the system. Yeah, but perhaps what people are more interested in is not here, where the energy, or rather tidal range is substantially reduced. You probably regulators will step in way before that and say you can take more out of it, right? So maybe it is up here that you'll be most concerned about. And in fact here, the error is actually quite large, because this initial curve is actually quite sensitive here. So I said 10%, but yeah, in fact that's the maximum physically extractable energy out of the system. And up here, the uncertainty might very well be greater. In this case, for instance, compared with this case and this case, about the same reduction in tidal amplitude, you have a very large, or certainly, factor of several difference in the amount of energy you can extract out of the system, or the estimate of energy you can extract out of the system. So 10% was the maximum, but in fact that might be a very optimistic number for the part of this energy extraction curves that actually matters. Yeah, I think we need a lot more research about this part. People have really focused on how much energy you can physically take out of the system, but really what really matters is this part of the regime, where you start taking energy out, and then, until you hit the regulatory limit of how much tidal reduction, you're allowed to make. Okay. Any other questions? How about remote folks? Anyone have questions?
Go back to put back on the.
Yeah. Which one?
Go down to go to weapon.
Yes.
And
okay.
hit the red button at the top.
Okay.
I think somebody there got a question.
Oh, do I have a question? I think you can also do, oh yes, there is a question here. So let's see if I can find it. Have you done those plots with tidal flow velocities instead of tidal range? No, I haven't. However, the plot will look very similar because tidal range is the two are closely tied because of mass conservation. So given that given tidal range implies a certain amount of water going in and out of the system, and that plus the cross-sectional area will basically set the velocity of the currents. So if I plotted the two, the tidal rain energy extraction against velocity values, the shape of the curve should look very similar. Of course, the numbers are going to be different, and that could be more useful measures for certain purposes. Any other questions? Yeah. Oh, I'm sorry that someone couldn't hear. I'm very, very sorry. I didn't catch that. Yeah.
So in different regions, there's actually plans to develop multiple plants. Fractions. So while you seem to show that the coastal models or estimation models are working well to extend that, there's some your full models having some interesting outcomes in terms of potential weak but long range differences.
Yeah. Yeah.
In cases where we're going to have from distant part of regions, perhaps across neighboring regions, different devices, how would you see these kind of weak differences interacting between devices? Would you expect multiplicative effects or additive effects in a longer range?
Yes. Yeah, good question. I think that in the case where the individual fields are non-resonant, probably effect will be simply additive, I think. The resonant case, though, is interesting because, as it turns out, if you do the maximum extraction experiment with resonant field and plot the change in the tidal amplitude in the open ocean, there's actually a substantial or noticeable change in the northwestern corner of the ocean basin as well. So in that case, the tail of the effect of the extraction could be quite long, and that was something again Chris Garrett found with regards to Fundy extraction experiment, which he showed could affect the tide in Boston Harbor, outside the mouth of, near the mouth of Gulf of Maine. So, in this, if you have any system that is close to resonance, I think that could affect the surrounding. Changes in that could affect the surrounding waterways significantly, I think. Yeah. Yeah.
I was quite intrigued. I put a lot of ABCPs on the seabed for a very long time. You've done studies on how your generation affects magnetic field and potentially the compass for the
no. Yes. Well, that's actually not, rather outside of my expertise areas. I'm not mainly an observational. Have you found any drifts in that kind of thing?
Well, we can calibrate them on the ship.
Yeah. Yeah.
So I was wondering how magnetic field would affect. Hopefully, you can calibrate for it. Anyway.
Okay. Yeah. So, magnetic fields. You probably know that magnetic fields can actually be used to measure current transport in an integrated sense. So that kind of thing might be useful for some purposes. Yeah. Anything else? Yeah. Yeah. I guess good. Yeah.
Complete left field question. Okay. I used to work in a fjord system where they put a hydroelectric plant at the end of it.
Yeah, yeah.
Increased the freshwater flow into the fjord system and increased stratification of freshwater. would it make sense to try and put some tidal devices at the sill to actually try to compensate or to kind of try to re-establish a normal circulation process?
After, yeah.
After, because of that excess in fresh water. Would it help?
Probably not for the interior of the fjord. I think that these tidal turbines can locally generate turbulence in its wake and enhance mixing locally, but I don't think for any size fjord I don't think that effect would propagate into the interior, but rather get dissipated in fairly close range within. So that means in the interior, if you put tidal energy device in, then it's energy, the less energy will become available in the interior for the mixing, which means the interior circulation will become more sluggish. It might actually enhance the exchange in the field channel outward of where the tidal energy device is, but if you put it at the head, that's where the current is minimal, so that's not where you would put a turbine in. So yeah, I don't think that's going to work. Okay.
Okay, I have one more question. I just was going to ask them to look at real data.
Yeah.
Once we have arrays in the water,
yeah.
What would you suggest is the best type of sampling? How far apart, how close together? What kind of sampling array should we have to see if these numbers are accurate?
I think that I think there might be a couple of questions there that are implied. One is a question of how do we know the amount of energy that is naturally dissipated in the system so that we can calibrate the model with it. There are ways to do that. For instance, for long field-like systems, it is shown that if you do a harmonic analysis of the tide and look at the phase change in the tide, that is a measure of the total amount of energy that is dissipated in the system. So you can put some envelope numbers on it that way. So probably the most useful kind of measurement in that would be some kind of tide gauge, or these days you can get fairly low-priced pressure gauges that you can leave in the water flow for a long period of time. If you have that throughout your tidal fjord, you might get a good constraint on how much energy is being expended that way. The other question I think is implied is how can we learn about the actual shape of this initial scaling? I think I'm not entirely sure. Other than that, it probably has to be done in reality as a sort of adaptive management program, so that you would develop this system to a certain scale, and then measure the energy. Well, you know what the energy extracted is, but you ought to be able to measure the tidal range fairly accurately if you have long enough deployments of tidal arrays. Let's say 1 year deployment should show an M2 tide parameter change fairly well if you have a good long-term time series of tidal range. So that kind of thing, again, shouldn't be too expensive. Would be very useful, at least as a constraining kind of measurement. And then you probably want to gain over several years time frame as your array develops. How this curve is taking shape. And once I think that's done, then probably you can match it to not even a model study, maybe even an analytical study to get a better feel of what this maximum is going to be like, or where to stop, before you reach that level. Yeah.
Well, I think we'll go to a close, so thank you again.
Okay, thank you.
See what we have to do with John here to do this.